So in this video, I'm going to talk you through the answers to the AS Paper 2 Stats and Mechanics for the sample assessment material. Okay, now I say stats and mechanics, I'm actually only going to talk you through the solutions for the mechanics questions. Now for each one, we'll start off with the question itself. So you can pause at that point if you want to have a go without a hint. We'll then move on to a hint. So I'll just sort of give you guidance on how to answer a question. So just sort of set you off for each of the key parts of the question. And then finally for each question, we'll then move on to a proper sort of work solution. So starting off in section B, the first stats question was question number 6. So this is the question if you want to pause and have a go without the hint. So here's the hint. So just draw in these dotted lines to help you gather your thoughts, and let's call that distance there h. Okay, now two things for here. This is a velocity time graph, so the gradient is the acceleration. Okay, so the gradient is the y step over the x step, so acceleration equals the y step, which is h, over the x step, which is t, and then just rearrange that to make h the subject. So that's part one of your thought process. The second thing to remember with a velocity time graph is that the area under the graph represents the distance. So the area under this graph is going to be this rectangle here plus this triangle here. So write down what they are in terms of u, t, and h. And then you can eliminate h by substituting in what you got from earlier on up here. So do that and you should be able to end up with what you had to show. So the solution for question 6. So as I said in the hint, the gradient of a velocity time graph is the acceleration. So that's going to be the y step, which is h, over the x step, which is t. And if we multiply both sides by t, we can make h the subject, so h equals at. So let's just park that for now. Now, the second thing we know for a velocity time graph is that the area under the graph represents the distance travelled. So that's going to be this triangle here, this rectangle here, plus the triangle here. So the rectangle is base times height, which is t times u, or u times t, and the area of the triangle is half times base times height, which is half times t times h. So that's what the distance is. Now I'm going to substitute in and replace h with at. So that's what I've done here. Multiply out the second term, we get what we needed, which is ut plus half at squared. Question 7. So the hint, here's a little diagram in blue of what's going on. So A to B is 22 meters, B to C is 104, and we get from A to B in 2 seconds, and we get from B to C in 4 seconds. So overall, getting from A to C is a distance of 126 meters, which takes us 6 seconds. Now, the key to answering this is to consider AB, but then also to consider A to C. Okay, now if we use s equals ut plus half at squared on both of these, our only unknowns are u and a. So we've got two equations, two unknowns. So substitute in for a to b and for a to c, and then use algebra to work out what u and a are. The solution for question 7. So going from A to B, it's a distance of 22, so S is 22 and the time is 2. So substituting that in and rearranging, I can make U the subject, U equals 11 minus A. So that's equation 1, which I'll just park for now. Now looking at going from A to C, a distance of 126 and a time of 6 seconds, I get this here. 126 equals 6u plus 18a. Now I'm then going to substitute in what I've got from before, that A is equal to, that U is equal to 11 minus A. So I'm replacing the U with 11 minus A. This allows me to solve for A and then substitute back in. I can then solve for U. So A is 5 meters per second squared and U is 6 meters per second. Question 8. Now, I think part A was quite difficult here. I mean, it's fair enough just to establish the two extremes. So if you substitute t being 0 into the displacement, the distance formula, and t being 10, excuse me, and substitute t being 10 into the distance formula, you will see on both occasions that the distance travelled is 0. So that explains why we are at the nest at both 0 and 10. Now, it's a little bit hard to justify how we don't return to the nest during those 10 seconds. So what you need to do is to first of all factorise and take the t squared out, and then realise that this is a difference between two squares. So this is a completing the square. So t squared minus 20t plus 100 is t minus 10 all squared. So really, once you've got that, you can see that between 0 and 10, that t squared is always going to be positive. T minus 10 all squared is always going to be positive. So S is always going to be positive. So greater than 0. So that shows that we don't return to the nest during that 10-second period. Now, for part B, find the distance of the bird from the nest. So we're not talking about just when we started. So it's left the nest. What's the first time that it comes to rest? Now, remember, when we're instantaneously at rest, this is a key point, the velocity equals 0. So whenever you have a question and it says you're instantaneously at rest, think velocity equals 0. So multiply out the distance equation to get a 10th t to the power of 4 and so on. Differentiate that, okay, and set that equal to 0, and you will get a number of times. You will get a number of times values for t, and then you want to take the first time after t being 0, and that will be your final answer. So the solution for question 8. Okay, so when we substitute t being 0 and t being 10 into the distance formula, we do indeed get distance of being 0. So that establishes the two extremes. We then really need to justify what's happening between those two extremes. So if we factorise and take the t squared out, we can then complete the square on t squared minus 20t plus 100. So we're left with distance being a 10th t squared, t minus 10 all squared. Now, between 0 and 10, t squared is always going to be greater than 0, and t minus 10 all squared will also be greater than 0. Therefore, the distance will be greater than 0. So we can establish that the bird does not return to the nest during the 10 seconds. Now, for part B, the key point here is that you're instantaneously at rest when the velocity equals 0. So multiply through by a 10th to get a displacement, a distance formula that we can differentiate. Differentiate it. So remember, you multiply by the current power, reduce the power by 1. That gives me this. And we want to set this velocity to being 0. So I've set it equal to 0 here. I've then factorised it, taken a t out, and then to simplify things, so I want to know when this equals 0. So obviously the first time is when t equals 0. Now, if I then focus on the bracket, I now need to solve the quadratic in the bracket, which I've taken up here. I've chosen to multiply through by 5 and divide by 2. That gives me a straightforward quadratic to factorise. I get t minus 10 and t minus 5. So my three occasions when the bird is at rest is at 0, 5 and 10. So I want to know the distance of the bird when the bird first comes to instantaneously rest, having left the nest. So that's going to be when t is 5. So it's initially in the nest. It leaves the nest for the first time, comes to rest, and then returns to the nest. So I want to substitute into the displacement formula when t equals 5. So subbing that into the distance formula, I get S being 62.5 meters. Question 9. So for the hint, I've given you the diagram. So remember, the two tensions point towards the pulley, and then we're told it's a rough table, and we're told that the resistance is 12.7. So obviously that's going to the left. It's resistance that's fighting against the movement, and we know that the weight of B is going to be 1.5 G. So we've got these four forces in play. 12.7 resistance, tension, 1.5 G weight. Now for A part 1, write down an equation of motion for A. So we're focusing on A, do it in the direction of motion, which is left to right, and then just substitute in to F equals ma. So what is the net force as you go from left to right? So that will give you the equation of motion for A. Now for A part 2, we're now looking at it from B's point of view, which is going downwards. So again, just resolve downwards using F equals ma and net off the forces the right way around. Which is greater? Is it the 1.5 G or the T, bearing in mind which direction the motion is in? Now for part B, to find the acceleration, you can just add together your two answers from part A. That will eliminate the tension, allowing you to work out the acceleration. And then for part C, use the model to find the time it takes from release for B to reach the floor. So what do we know? We know the distance travelled by B is going to be 1, so S equals 1. We know the acceleration from part B of our answer. We're starting from rest, so U equals 0, and we need to work out T. So use the appropriate Suvat equation to work out what T is, given you know S, A, and U. So the solution for question 9. So the diagram as per hint. The hint, now from the point of view of A, we're resolving left to right. F equals ma. Now because we're moving to the right, the tension must be the greater force than the resistance. So our net force is going to be T minus the 12.7. So that's our F. Our mass is 2.5, and we don't know the acceleration. Now for A part 2, we're resolving for B in the direction of motion, which is downwards. Now because we're going downwards, the 1.5 G weight must be greater than the tension, otherwise we'll be going upwards. So this is 1.5 G minus T, that's our net force, equals our mass of 1.5 times the acceleration. Now for part B, to find the acceleration, just add together equations 1 and 2 up here. Okay, so adding these together, we get 1.5 G minus 12.7 equals 4A. Make A the subject, and we get 0.5 meters per second squared. Now for part C, we're going to use Suvat. So the distance we're traveling is 1 meter. Our acceleration from part B is 0.5. Our initial speed, where we were going from rest, so U equals 0, and we need to work out what T is. So using S equals UT plus half AT squared, we can solve to find that T is 2. Now for part D, suggest 2 improvements that we could make to the model. So I've just copied and pasted this from the answers. So you could include the dimensions of the ball in the model so that the distance it falls changes. You can include the dimensions of the pulley in the model, so the string is not parallel to the table. You could include a variable resistance in the model instead of taking it to be constant. You could include a more accurate value for G in the model.